Okay, let's unpack this. Picture a molecule, right? Maybe something familiar like caffeine, or maybe a totally new drug compound.
Mm.
If you're a chemist, you look at its structure, maybe draw it out, and you sort of intuitively get how it connects, maybe how it behaves, how it might fold up.
Yeah, there's a chemical intuition there.
Exactly. But now you want AI to work with that molecule. Maybe, predict its properties, search for similar ones, design new versions.
Right.
A computer, it's amazing with numbers,
Yeah.
but it doesn't understand Lewis structures or that intuition. It needs numbers. Rigid, unambiguous, machine-readable data.
And that translation, taking this, complex, sometimes kind of squishy 3D reality of a molecule and turning it into the digital language a computer gets, it's not just some technical step. It's, well, arguably, it's the most fundamental challenge in applying AI to chemistry.
Welcome to the Deep Dive.
Oh.
Today, we're diving headfirst into exactly this problem. How do we speak the language of molecules to machines?
And we've got a really great set of sources to guide us here. A study guide, answer keys, some essay questions, a glossary, briefing notes, all focused on this molecular representation for AI. These are the specific materials you provided for us to explore today. So our mission really is to use these sources to unpack the main ways we translate molecules for computers, understand why getting this right is just absolutely critical, and look at the trade-offs. Because they're all always trade-offs.
And trust me, this really matters. Whether you're aiming to speed up drug discovery, find new sustainable materials, or even just trying to follow the cutting edge of AI and science, getting this translation right is probably the single most vital step in any chemical AI project.
That's absolutely right. Often more important, actually, than the fancy AI algorithm itself. The sources hammer this home right away. Garbage in, garbage out, GI go. It applies with real force here.
Yeah.
If the way you describe the molecule to the AI is just poor or incomplete, or maybe misses the key info for your specific problem, well, then the AI's output is going to be bad. Simple as that.
The sources put it pretty bluntly, saying something like, poor representation can render even the most sophisticated algorithms ineffective.
While a good one can unlock profound insights.
Exactly. This translation isn't just about formatting data. It's about encoding the relevant chemical information so the machine can actually learn something useful. That's the starting point for everything else.
Okay, so let's dig into that a bit more. Why is this molecular representation, this language, so utterly fundamental?
Well, like we said, chemists have their ways, drawings, physical models, that intuition. But computers don't read minds or drawings easily. AI needs numerical input. So the very first hurdle is always converting that chemical structure into numbers, or maybe binary data. We can sometimes call it featurization or encoding. It's the bridge between the chemical world and the digital world AI lives in.
And if that bridge is, like, wobbly.
Then GI-GO hits you right away.
Yeah.
If you're trying to train an AI to predict, say, how well a drug binds to a target protein, but your molecular representation totally ignores 3D shape or chirality handedness, which is often crucial for binding,
Right.
then even the smartest deep learning model is going to fail. It just wasn't given the right words, the right kind of information to learn the relevant chemical sentence.
Okay, so capturing the right information is absolutely key. What are the main strategies we've developed for this translation? The sources lay out a few big ones. Let's maybe start with what seems simplest. Just a line of text.
Right. That would be SMILES. Stands for Simplified Molecular Input Line Entry System. Developed way back in the 80s by David Weininger. It's basically a way to write down the 2D structure using just standard keyboard characters, ASCII characters.
So, like, literally writing out the atoms and bonds in a line.
Pretty much. Use atomic symbols like C for carbon, O for oxygen. Parentheses show branches, numbers show where rings close up. And a neat detail the sources point out is using lowercase letters like C for aromatic atoms, like in benzene. That captures some electronic info right there in the string. It can encode stereochemistry too, the 3D arrangement around certain atoms, but that adds complexity with special symbols like added signs or slashes. So what makes SMILES useful? Why did it catch on?
Well, for one, they're super compact, great for storing huge databases of molecules, and they became really widely adopted, so lots of software and databases use them. They're kind of a common language. And being text strings, machines can process them, especially if you break them down into smaller pieces, tokens. That makes them usable for certain AI models, like sequence models, that are good with text.
But you mentioned a catch earlier. Something about uniqueness.
Ah, yes. This is a really crucial point and a big limitation if you're not careful. A single molecule, like ethanol, can be written in multiple ways using Smiles rules. CCO works, OCC works, COC works. They all describe ethanol.
Right, but the computer needs to know they're the same thing.
Exactly. So for reliable use, you need one standard version. That's where canonicalization algorithms come in. They take any valid Smiles for a molecule and crunch it down into a single unique canonical Smiles. Now, you do have to be a bit careful because different software tools might have slightly different rules and produce slightly different canonical forms, but the goal is always uniqueness. The other thing is, standard Smiles is mostly about the 2D connections. 3D info isn't really baked in.
Got it. So Smiles is the linear code, compact but needs canonicalization and is mainly 2D. What about summarizing the molecule differently, like just listing its properties?
Right. That takes us to molecular descriptors. Here, the idea isn't to encode the whole structure directly, but to sort of boil the molecule down into a set of numbers that quantify its characteristics. You end up with a fixed-length list of vector of numerical values.
So numbers representing things like size, or how much it likes water versus fat.
Precisely. The sources categorize them nicely. You've got 0D descriptors based just on the formula like molecular weight, number of carbons. 1D descriptors count fragments like how many hydroxyl groups it has. 2D use the connectivity graph things about branching or size. And 3D descriptors use the 3D shape or calculated electronic properties, things like log P, which measures fat solubility, or surface area.
What's the big advantage of using these descriptors?
Well, a huge strength, probably the key strength for many of them, is interpretability. A chemist looks at a log Pa value, or a molecular weight, or a count of hydrogen bond donors, and they immediately understand what that number means chemically.
Right, it connects to their intuition.
Exactly. So models built using descriptors are often easier for chemists to understand, to rationalize why the model made a certain prediction. Plus, they're generally pretty fast to calculate, especially the 0D to 2D ones. There are great tools like RDKit or Padel Descriptor that do this easily. And historically, they've been really successful in QOR and QSPR, quantitative structure activity or property relationships.
Okay, makes sense. But what's the downside? What do you lose?
The major weakness is that they're inherently lossy. You're summarizing, right? So you're throwing away a lot of the detailed structural information. And this leads to a critical issue, the sources flag. The isomer problem. Many simple descriptors just can't tell the difference between isomers molecules with the same formula but different structures. And this is especially bad for stereoisomers, like enantiomers. Same atoms, same connections, just arranged differently in 3D space, like mirror images.
And that difference can be huge biologically.
Huge. Life and death huge sometimes. The thalidomide tragedy is the classic heartbreaking example implied here. One stereoisomer was helpful, the other caused devastating birth defects. Many descriptors would see those two molecules as identical. They just don't capture that crucial 3D difference. Also, 3D descriptors depend on the conformation, the specific 3D shape you calculate them from, and descriptors can often be highly correlated with each other, which can mess with AI models.
Okay, so descriptors. Interpretable properties, but they lose vital structural detail, especially for isomers and 3D shape. What about trying to capture structure more like a checklist? Like, does it have this piece? Does it have that piece?
Yeah, that's a great analogy for molecular fingerprints. The idea here is to create a binary string, just a long list of zeros and ones, where each position, each bit, tells you whether a specific chemical feature or substructure is present, a 1, or absent, a 0. It's like running down a checklist.
Is there just one kind of checklist or different types?
The sources highlight two main kinds. First, you have substructure keys, sometimes called dictionary-based fingerprints. Here, each bit position is explicitly tied to a predefined chemical query. Like bit 5 asks, does it have an ester group? Bit 12 asks, is there a sulfur-sulfur bond? Bit 30 asks, does it contain a benzene ring? MAC-CS keys are a common example, with 166 predefined structural questions.
So with those, you know exactly what feature flipping a bit means.
Exactly, that's their big advantage. They're relatively interpretable. You can often point to the substructure that turned a bit on. They're also pretty fast to compute. The main limitation is, well, you're limited by your dictionary. If your molecule has some weird novel feature that isn't in the predefined list, the fingerprint just won't see it.
Okay. And what's the other type of fingerprint?
The other main approach is hashed fingerprints. These are often called topological or path-based or circular fingerprints. Big examples are ECFP extended connectivity fingerprints or Morgan fingerprints. Here, instead of a fixed dictionary, the algorithm finds structural features directly from the molecule itself.
How does it find them?
It typically explores the molecule's connectivity, like ECFP starts at each atom and looks at its immediate neighbors, then the neighbors of neighbors, and so on, creating identifiers for these circular environments. Or other types might look at paths of atoms and bonds. Then, and this is the key part, it takes these discovered features and uses a hashing function to squash them down and map them onto bit positions in a fixed-length vector.
Hashing. So it takes potentially tons of different features and fits them into, say, 10 and 24 bits.
Exactly. That's the power. They can capture a huge amount of detailed local structural information. The sources say they can represent an essentially infinite number of different molecular features because they're generated on the fly from the molecule.
That sounds really powerful for catching subtle differences.
It often is. They tend to perform very well in prediction tasks. But the major drawback is the flip side of hashing interpretability. Because many different structural features might get hashed to the same bit position, you generally can't just look at bit 512 being on and know exactly which specific structural environment caused it, not without special tools to try and backtrack.
And you could have bit collisions, right? Where two different important features end up flipping the same bit.
Precisely. That's the risk with hashing. You can lose some information if different features collide onto the same bit.
Okay, so we've got linear codes, smiles, property lists, descriptors, binary checklists, fingerprints, both dictionary and hashed. It still feels like we're kind of approximating the molecule. What about representing the structure? Well, as a structure.
That leads us directly to molecular graphs, and the sources really emphasize this, calling it perhaps the most natural representation for molecules in AI. Because, I mean, think about it. A molecule is a graph, fundamentally. Atoms are the nodes, the vertices. Bonds are the edges connecting them.
So the data is the structure itself, basically.
Essentially, yes.
Right.
And you can enrich it. Each node, each atom carries its own set of features like atomic number, charge, maybe its chirality. Each edge, each bond also carries features like bond type, single, double, aromatic, whether it's in a ring.
How do AI models actually use this graph structure then?
This is where graph neural networks, or GNNs, are a game changer. GNNs are a type of deep learning specifically designed for graph data. The core idea, often called message passing, is really cool. Atoms, the nodes, send messages to their direct neighbors across the bonds, the edges.
Like atoms talking to each other.
Kind of. Each atom gathers the messages from its neighbors, combines that information with its own features, and then updates its own state or representation. This happens iteratively over multiple layers. So information effectively flows through the graph, through the chemical bonds, allowing the GNN to learn really complex patterns and relationships across the whole molecule.
That sounds like it lets the AI see the connections much more directly.
It does. It's often described as a paradigm shift because it moves away from needing chemists to manually engineer features like picking the right descriptors or designing fingerprint dictionaries. The GNN can potentially learn the most relevant structural features directly from the graph data itself.
So what are the main advantages of using molecular graphs, especially with GNNs?
Well, the graph representation itself can be potentially lossless for the 2D structure, not really throwing information away there. And you can easily add 3D information too, like atomic coordinates, as node features. This richness gives the AI a much more complete picture. And this enables these powerful GNNs to learn very complex, subtle structure-property relationships that might be missed by simpler methods.
Okay, sounds very powerful. Are there downsides?
Training these complex GNNs can definitely be more computationally intensive than using, say, descriptors or simple fingerprints, especially with very large data sets. Although just building the graph itself is usually super fast. And while the input features, like atomic number, are clear, figuring out exactly why a trained GNN made a certain prediction, tracing the flow of information through all those message passing steps, that can still be challenging for interpretability depending on the GNN design. It's not always as straightforward as looking at a single descriptor value.
Right. So we've walked through smiles, descriptors, fingerprints, substructure and hashed, and now molecular graphs with GNNs. That's quite a menu of options. How on earth do you choose which language to use for a given problem?
Yeah, and this is where the sources bring up the no free lunch theorem explicitly. It's absolutely key. There's no single representation that's the magic bullet, the best choice for every single chemical AI task. It's always a matter of trade-offs.
What are the main trade-offs we're juggling?
You're balancing information richness, how much detail about the molecule does it capture? Graphs are typically highest, simple descriptors lowest. You balance that against computational cost. GNNs can be heavy to train, descriptors are usually cheap. Then there's the classic tension, predictive power versus interpretability.
Hmm.
Hash fingerprints and GNNs often give higher accuracy, but understanding why can be harder than with interpretable descriptors or substructure keys. And crucially, how well does it handle isomers, especially stereoisomers? Graphs, if you encode chirality properly, are generally best here. Descriptors are often the worst.
So the best choice really isn't absolute. It depends entirely on the specific question you're asking the AI, what kind of data you actually have, and what outcome you need. Is it pure prediction, or do you need to understand the chemistry behind it?
Exactly that. It's probably one of the most critical design decisions you make right at the start of any project in this space.
Can we ground this with a couple of big, real-world examples where getting the representation right was clearly fundamental to a major success?
Absolutely. The sources point to a couple of really great ones. First, the discovery of halicin, remember that? The first antibiotic found using deep learning by the MIT team.
Yeah, that made big headlines.
Right. The deep learning model was key, of course, but its success was totally dependent on being fed molecular data represented by, essentially, chemical features. This effective featurization allowed the model to learn the patterns linked to antibiotic activity from thousands of known molecules and then screen a huge library to pinpoint halicin. The AI learned from that specific language of features.
Wow, a new antibiotic class, basically enabled by the right representation.
Fundamentally. And another huge one, AlphaFold 2. DeepMind's breakthrough in protein structure prediction.
Oh yeah, revolutionary.
It didn't just use the simple amino acid sequence. Its incredible accuracy relied heavily on a very sophisticated graph-like representation. It included the sequence, yes, but also rich evolutionary information from comparing many related protein sequences, multiple sequence alignments, and other structural information. That specific, carefully crafted input representation was absolutely vital for their complex AI to work its magic.
Those are fantastic examples. It really drives home how this initial step, this translation choice, isn't just technical detail, it's foundational to these massive scientific advances.
It really underscores the point.
Yeah.
The representation isn't just the plumbing, it's the bedrock upon which AI success in chemistry is built. You get it wrong, the whole structure's shaky.
So wrapping up our deep dive today, we've journeyed through these different molecular languages, from simple text strings like smiles and property summaries like descriptors, to these binary feature checklists and fingerprints, and finally to the rich structure-mimicking molecular graphs used by GNNs. And we've seen that each has its place, its pros and cons, critical trade-offs involving information, cost, interpretability, and handling tricky things like isomers. Choosing wisely is paramount.
And understanding these different ways molecules talk to machines, it's not just for the hardcore AI developers anymore. It's becoming essential knowledge for anyone in chemistry, materials, biology who wants to really leverage AI or even just critically evaluate the AI-driven results they see.
It really highlights that intersection of deep chemistry knowledge and computational thinking, which actually leads to a final thought to maybe leave our listeners with. Given the power we're seeing, especially with molecular graphs and GNNs, where the AI learns directly from the structure, almost like it's learning chemical rules from the data itself through this message passing. Could we eventually reach a point where AI learns so deeply from this natural graph language that it starts proposing truly novel molecules, maybe even entirely new types of chemical reactions, that are way outside what a human chemist working with our traditional models and intuition might even conceive of?
Ooh, that's a fascinating and kind of provocative question. It really opens up possibilities about the future of chemical creativity, doesn't it? The interplay between human insight and what these powerful algorithms might discover on their own.
Definitely something to mull over. Thank you for joining us for this deep dive into the language of molecules for AI.